In the previous video, I showed you a demonstration to illustrate that pressure in a liquid increases as you go deeper into the liquid. In this video, we're going to try to understand why that is. Before we get into that, though, there are a couple basic concepts related to fluids that I want to remind you of. First, we have the idea of pressure. Here's the idea of pressure. Suppose we take a surface and insert the surface into a fluid. What's going to happen then is that particles in the fluid are going to strike the surface and bounce off, strike the surface and bounce off. The net effect of those collisions is to exert a force on the surface perpendicular to the surface. The pressure in the fluid is the ratio of that force to the area of the surface. I've also introduced you to the density. The density is the ratio of a mass of some piece of material to its volume. Now let's get to the question of why pressure increases as you go deeper into a fluid. In this figure here, I've drawn a tank which has been filled with a liquid of constant density rho. Also, the pressure of the liquid is P sub 0 at the top surface of the liquid. I have also marked out two columns of the liquid, here and here, within the larger body of the liquid. So these rectangular shapes that I've drawn here and here do not represent physical things that I have stuck into the liquid. Rather, these rectangular shapes represent imaginary boundaries separating smaller regions in the liquid from the larger liquid. Let's look at this column on the left. I drew this column on the left by marking off an area A at the top surface of the tank, and then going into the liquid by a depth H1. For the column on the right, I marked off an equal area A at the top surface of the liquid, but this time I went deeper into the liquid by a depth H2. Now we'd like to understand why pressure increases as a function of depth as you go deeper into a liquid. So to do this, let's start by drawing force diagrams for each of the liquid columns. Let's start with the column on the left. For the column on the left, there are three forces acting. First, I have the force associated with air pressure pushing down on the top surface. I'm going to call this force F sub ATM. That's the force of the atmosphere pushing down on that top surface. Then I have the gravitational force acting on that specific blob of the liquid. I'm going to call this G1. Notice that I now have two downward forces. I have the force from atmospheric pressure pushing down on the top surface. I have the weight of the liquid column. So these two need to be balanced by an upward force. What would that upward force be? Well, that upward force would be the force from the liquid pressure pushing up on the bottom surface. Let's call this force from the liquid pushing upward on the bottom surface F liquid. Now let's do that same force balance for that deeper column on the right. I'm going to have the same three forces acting. First, I'm going to have the force from the atmosphere pushing down on that top surface. And I will again call that F atmosphere. Before I proceed further, what would be the magnitude of either of these forces? Well, let's come over here and look at our formula for pressure. Pressure is defined as force over area, and we know that the pressure at the top surface of the liquid is P0. So what then would be the magnitude of this force from the atmosphere pushing down? Well, if I solve this equation for force, I get pressure times area. And the pressure pushing down on that top surface would be P0. So the force from the atmosphere pushing down here would be P0A. And the force from the atmosphere pushing down over here would be the exact same expression, P0A. So you can see that these two forces here and here are equally strong. Continuing now with this column on the right, there would also be a gravitational force pulling down on this column. Now, would the gravitational force pulling down on this column be stronger, weaker, or the same compared to the one over here? Well, if you look at this column, you can see that it's bigger. There is more fluid mass in there, so the gravitational force is going to be bigger. Now, this column on the right is going to have a force from liquid pressure pushing up on the bottom, just like this column on the left. However, when I draw the force of liquid pressure pushing up on the bottom of this column, is that force going to be stronger, weaker, or equally strong to the force of the liquid pushing up over here? Maybe pause the video, contemplate that, and when you think you have an answer, maybe put that into your own notes and then rejoin the video. The force of liquid pressure pushing up on the bottom of the right column has to be bigger than the force of liquid pressure pushing up on the bottom of the left column. While both of these forces from liquid pressure are balancing equally strong forces of atmospheric pressure pushing down on the top, this column on the right also weighs more because it's a bigger column. And because this column weighs more, we need a bigger upward force on the bottom to balance that bigger gravitational force. How can the force from liquid pressure here be bigger than the force from liquid pressure here? Well, let's use the formula again that force is equal to pressure times area. Let's say that the magnitude of this force over here is pressure 1 times the area. Let's say that the magnitude of this force over here is pressure 2 times the area. Can you see that in order for the force here to be stronger than the force here, that means that the pressure at the bottom of this column has to be bigger than the pressure at the bottom of this column? Can you see then that pressure 2 has to be greater than pressure 1? So this is why pressure increases with depth. Pressure increases with depth because the deeper you are in the liquid, the more stuff that you have above you that has to be supported by the pressure at that level. When you are shallow in the liquid, the pressure only has to support a little bit of liquid above, which means that you don't need that much pressure. But as you go deeper into the liquid, the pressure at that level has a lot more stuff above it that has to be supported, so the pressure would be greater. So I hope that through this video, you've been able to understand why pressure in a liquid increases with depth. In the next video, we're going to derive a formula which describes quantitatively the manner in which pressure increases with depth.